hinges. So we will look at how to consider beam example where there are internal hinges. So class, I am showing you now a 3-span beam with 2 internal hinges. One is here between this support and this support at the first span, and another one, if you look at the span number 1, span number 2, span number 3, so in between the third span, so this is span 1, span 2, span 3, so there is another hinge. So this is a 3-span beam with 2 internal hinges, or this is a continuous beam. This is a continuous beam. We have more than 1 span, so it is a continuous beam with 3 span, and there are 2 internal hinges. And I call this case 1. Later on, we are going to look at case 2, where also 2 internal hinges, but the location of hinges is different. So, but anyway, these 2 cases that we are going to look at, there are examples of beams with internal hinges. So when the internal hinges, there must be something that we need to do extra. Okay, so there are UDL 5 kN per meter along this span, and 3 kN per meter UDL along these 2 span. The distance here is 40 meter, and the hinge is 20 meter from this left support. The center span is 50 meter, and the last span is also 40 meter with a hinge here. So we draw a free body diagram of the whole hinge. If we draw the free body diagram of the whole of this 3-span beam, so you get 2 reaction support because this is pin, roller, roller, roller. So there are 5 here. And let's check for statical determinacy. So class, when we check for statical determinacy, remember if there are hinges, then we have to we have to separate the beam at the location of the hinges. So there are 2 hinges, so we separate them, so we get 3 parts. So beam problem with internal. So we separate them when we want to check statical determinacy. So we separate them because there are 2 hinges. So we separate them at the 2 hinges there. So you get 3 parts here. Hinges here. So we have part 1 AB, part 2 BE, part 3 EF here. So how many unknown forces we count now? R is 1, 2. The red one, there are the internal forces at hinge. So 1, 2, 3, 4. Don't count this 5, 6. Okay, because they are the same magnitude, only direction different. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the blue one we have 1, 2, 3, 4, 5. And the red one, which is we separate at the internal hinges, internal forces appear, you get additional 4. So 5 the blue one, 4 the red one, so you get 9. Equilibrium equations, we have separate these beams, 3-span beam into 3 parts. So each part we have 3 equilibrium equations. So 3 multiplied with 3, we get 9. So this is actually statically determinate beam. So this is to refresh how we check statical determinacy of structures with hinges. So next, we have to solve. What we need to solve, class, we also need to remember what we are asked to solve is to get support reactions AX, AY, CY, DY, and FY. We are not asked to solve for BX and BY. So we do not have to worry what is BX and BY, but when we check statical determinacy, we need to consider them. We want to determine the blue one, the support reactions. So there are 5. 1, 2, 3, 4, 5. So let's see how to solve them. So support reactions. So the first equilibrium equation that we can use for the whole beam here, for the whole beam, if you look at the shear free body diagram for the whole 3-span beam, so we get this free body diagram. and immediately we can see AX is equal to 0 because there is no other load with horizontal component, so we get AX is equal to 0. We get AX is equal to 0. So this one is the first one we already solved. This is the first one that we already solved. So next, we go to the other support reactions that we want to solve, which is AY, CY, DY, and F. And there are 4. So how do we solve this? The next thing is the particular steps that we use when we have hinges. The first thing is we look at span A and B when there are hinges. And what we do here is we take the free body diagram of A, B only, which is we cut here. We cut here at the hinge here. Then we get this free body diagram. AX here already equal to 0, so we don't show here. AX is equal to 0, so we don't show here. And BX and BY appear here because there are hinges. There are hinges here. When we separate them, then you get the internal force. But what we want to calculate is AY. So we find an equilibrium equation that we can get AY. We are not interested to find BY and BX. It's not asked. We want to find AY. So in order to find AY, so now we take moment equilibrium, considering this free body diagram where we already cut at the hinge and make them equal to 0. But class, you pay attention when we do the cutting here, and we use this free body diagram here, and when we take moment at point B, we put a special symbol here, we put a special notation here, AB. Summation of moment at B equal to 0, but we consider only the AB part. This is to differentiate with this moment equilibrium equation. This moment equilibrium equation is considering the whole beam. But now we are not taking the whole beam, we cut here, then we use this free body diagram, then we take moment at B here at the hinge here should be equal to 0. Summation of moment should be equal to 0, but we considering only part AB which we already cut from this beam here at the location of the first hinge. So that's why we introduce this symbol. Okay, so there's one particular aspect that you have to pay attention. When you cut at the hinge, then we only consider that part which already cut out this free body diagram, and we take moment at B equal to 0 only for that part AB. Then we have to introduce this particular superscript here. Summation moment at B equal to 0, but we consider only part AB like this. So the rest is the same. So AY, negative AY 20, because I consider counterclockwise as positive. So AY is causing positive moment at B. So AY multiplied with 20 plus, this is distributed load, 5 multiplied with 20 multiplied with 10. Because this is UDL, so the equivalent force is acting at the center here. So the perpendicular distance to point B is 20 over 2, so 10. So you solve this, you get AY equal to 50. You get AY is equal to 50 class. So this is one particular steps where we are dealing with problem with hinges. When we are dealing with problem with hinges. Now, let's proceed. We already solved for one, AY, so there are 3 more. So now, look at the other side. Look at this side here. Look at this side here, the last span, the third span. We do the same thing. We cut here, we cut at the hinge here, then we get this free body diagram which is showing EF, part EF only, and EX and EY appear because these are internal forces at the hinge. But I emphasize we want to calculate this. We are not interested in this and this. So now, following the same step, we take moment equilibrium equations at point E, considering only this part EF, make them equal to 0. So we write down the moment equilibrium equations. This is due to this distributed load. This is causing clockwise moment at E. So become negative because I consider counterclockwise as positive. Then Fy is causing counterclockwise moment at E. So Fy multiplied with 20 give us the moment caused by this at point E. So we solve for this, then you get Fy equal to 30 positive going up. So Ay, Fy solve by using the free body diagram that we cut at the hinge. So next, we go back to the whole beam now. Whole beam, Ay is soft, Fy is soft. So we are left with Cy and Dy. There are two here, two. So we can take moment equilibrium equation now of the whole beam. When we take moment equilibrium equation of the whole beam, we do not cut at the hinge, then we do not put anything here. If you compare this and this, or this, the difference is, this is, we don't put any superscript here, because now we are considering the whole beam now. So you take moment at D, you can find Cy. So you take moment at D, you find Cy. Then again, I consider counterclockwise as positive. So this negative 50, 90 come from Ay at D. Then 540, 5 multiplied with 40. So this is the equivalent force due to this distributed load. And this is UDL. So it is acting at the center of this distance here. So which is, so this is 20. So you want to take moment at D, this is 50, this is 50 here. So 20 plus 50 gives us 70, which is the perpendicular distance from this equivalent force of this UDL to point D, the perpendicular distance. So next, Cy is 50. Cy is the force that we want to find. So Cy is causing counterclockwise. Cy is causing clockwise moment at D. So it becomes negative. Then the third one, the last one here, this is not the last one. The third, the 1, 2, 3, 4. The fourth one here is coming from this UDL, which is acting from C all the way until F. All the way until F. And this is UDL, so it's acting at the center here of this distance. This distance is, this is 50, this is 40, this whole thing is 90. This whole thing is 90 meter, 90 meter. And this is UDL, so this force here is acting at the center, is acting at the center. Is acting at the center, so it is at the center means it is equal to this is 90 acting at the center, this is 45 meter. So but this is where you have to keep in mind, you want to take moment at D, you want to take moment at D. So this is 45. And from here, CD, the distance is 50. So 50 minus 45, so you get 5 meter. So this is the perpendicular distance of this force equivalent to this distributed load to point D, which is 5. And it is causing counterclockwise moment at D. It's causing counterclockwise moment at D, that's why it's positive, because we consider counterclockwise as positive. And finally, this 30 at D, again causing counterclockwise moment at D, so 30 multiplied with 40. So we get the final terms here. And then all this make it equal to 0, then we solve for Cy equal to 241 positive, which is going up as we assume. So here is again applying the basic principle of moment. Don't forget what is moment, how to consider moment due to distributed load. And it must be, you must use the correct perpendicular distance, and perpendicular distance is decided from the point of action of the loading to the point where you want to take moment. So lastly, this one already decided, this one decided, this one decided. So only last one, this is what we have to calculate. So we make use of summation of forces in y directions, which is in vertical forces. So this one plus this one plus this one plus this one would be equal to minus this equal to 0. So 50 minus 540 is this, plus 241 minus 3 times 90 is this, plus dy plus 30. So finally we solve dy also positive 149. So with this we solve for all ay, cy, dy and fy. So remember these are the question asked. It does not ask us to find what is the internal force here. So it will be important to remember that, so that you don't spend time trying to find what is Vy, Vx, because that is not what the question wants. The question one, what is this, what is this, what is this, what is this, and also the Ax, which is already calculated as equal to 0. So checking, finally checking. So if this is a step for us to know whether our answer is correct or no. So you take moment at F. Any point that you haven't used, take moment at F, considering the whole beam here, then they should be equal to 0, approximately equal to 0. So that is to verify, to check that our answer that we obtain for the support reactions from our questions are reasonable and are correct. So this is one example of beams with hinges. And we need to take note of the existence of hinges in the solution process. Next, we are going to look at another example with hinges, but then also two hinges, but then the location of hinges changes. And because of that, there is extra things that we need to do, but the basic solution principle, the steps are the same, only there are additional calculations needed as a result of location of hinges changes. So this is case number 2. Case number 2, different from case 1, of course, other than the and also the distance and the span length A to B, E to F is 37.5. Here also 37.5. Just now we have 40, and the center span here is different. Just now we have center span 50, now center span is 45 plus 50, 90 now. Okay. And the hinges, just now it was here at the first span and the end span. Now the two hinges concentrated at the middle span. And the loading here also slightly different conditions. But the main thing that we like to emphasize between case 1 and case 2 is the location of the two hinges are different, and as a result, as I mentioned, we will see later, it will cause additional calculations, which makes the process a bit more lengthy. So first we draw case 1 and case 2. This is what I compare, case 1 and case 2, hinges in the first span and the third span. This is continuous beam with 3 span, both are 3 span. But case 2 is both hinges are concentrated on the middle span. Then free body diagram, if you want to check statical determinacy, so by now you should remember if there are hinges plus, you have to cut at the hinges there. So you get these 3 parts of, after you separate them at the 2 hinges and then show all the unknown forces, the red one. And the green one here now, the green one are the internal forces at the hinges after you cut them. So how many unknown forces? The red one, 1, 2, 3, 4, 5, and the green one again 4. So you have unknown forces, there are 9, equilibrium equation, 3 parts. So each of the parts, there are 3 equilibrium equations, so you get 9 equilibrium equations. So conclusion, this is statically determinate beam, same as case 1. So in terms of statical determinacy, both are statically determinate. So next, we do the same thing. We want to calculate, these are beams with hinges, so we have to make use of the hinges. We have to make use of the hinges. And the first equations that we use is we considering the whole beam, and then we take forces in x direction equal to 0, so immediately we get AX is equal to 0, because there's no loading in x directions. So support reaction AX is equal to 0. Only when there is a loading in x direction, then we are going to get AX at some value. In this particular case, because there's no loading with component in x direction, so we don't get any support reaction in x direction at A. So that is the first one solved. So we have another 4, which is AY, BY, CY, and all the vertical reaction force. And the first one solved, AX is equal to 0, so AY, BY, EY, and FY. So these are the 4 that we need to solve. So we cut at the hinge, same thing. We cut at the hinge first, then we cut at the hinge, then we cut at the hinge, okay? Then we cut at the hinge again, show the free body diagram, and then from there try to write down equilibrium equations. So let's see here, the first cutting here. The first cutting that we have done by cutting at the hinge at C here, and then we draw this free body diagram, which is to the left-hand side of the cut. So we draw free body diagram of A, B, C. Then we show all with the unknown forces Cx and Cy. What we want to calculate, class, is Ay and By. So now there are 2 unknown forces now. There are 2 unknown forces now. So if we follow the same procedures, you take moment at hinge here and make them equal to 0, but we put this superscript here AC because, as in the previous example, we consider only part AC. We only consider part AC. So because there are 2 unknown forces here, so if we write down equilibrium equation, we consider moment caused by all the forces, the red one here and the blue one, then you are going to get to these equations. So remember, class, I mentioned to you, as far as you can, try to find one equilibrium equations where from that equilibrium equations you can solve the unknown forces directly, which means there's only one unknown forces in that equilibrium equations. We try to find that, but in this particular case it's impossible, and we end up with an equation with 2 unknown support reactions, AY and BY. So we call this equation 1. So to solve this and this, we need another equations involving AY and BY. Where do we find this? This is the next one. We cut at the second hinge there. We cut at the second hinge there, which is at hinge D, and we draw the free body diagram of the left-hand side of the cut, where you see AY, BY appear again, and DX, DY also appear because we cut there. So the internal forces appear. Then we take moment equilibrium equations. We take moment at D again at the hinge. What we want to find is AY and BY. Then we take moment at the hinge again. We take moment at the hinge again. Put this superscript because we consider part AD only, where we cut at the hinge. So if you write down the equilibrium equation considering all the forces causing moment at D, so we come to these equations. And we notice that you have AY and BY again here. And we call this equation number 2. So together with equation number 1, we solve this simultaneously, and we have AY negative 452, which means that the direction is opposite to what we assume, and BY is positive going up. So this is one difference from case 1, where case 1, we did not need to solve simultaneous equation because we can get the unknown forces directly from one equations. But in this case number 2, because of the location of the hinges, which is changes from the first span and the third span to 2 concentrate on the mid span, so we cannot get AY or BY or any other forces directly. Instead, we have to solve simultaneous equations. So this is one of the things that we like you to be aware of, because sometimes because of the changes in location of the hinge, so the calculation process will be a bit more lengthy because you need to solve simultaneous equations. Of course, the basic principle used is still equilibrium. So now we have already decided this AY is 452. Now take note that already indicated here as the correct directions. Initially we put going up, but we found that is negative, so already indicated there as the correct direction going downwards, BY going up. So there are 2 remain, EY and FY. So take the similar process, take moment at F, we find E. But here we take moment equilibrium equation of the whole beam. We take moment equilibrium equation of the whole beam. Then if we write down the equilibrium equations, now this is where you need to apply the correct principle of moment caused by all the forces, including all the support reactions and this distributed load at point F. Okay, at point F. Then we will get EY 3696 kilonewton. Positive means direction that we assume going up is correct. Direction that we assume going up is correct. Okay. So take note of this particular part, which is 44 multiplied with 105, corresponding to this UDL, the total loads, and then 105 over 2. This whole thing is 105, and the corresponding load is acting at the center here. So we want to take moment at F. That's why 105 over 2 gives you the moment, and it is counterclockwise. That's why it becomes positive. So you have to familiarize yourself of this, how to consider moment caused by UDL. So finally, EY is left. So EY is left, FY already decided, EY already decided. So only FY is left. So use this equilibrium equation of forces in Y direction, considering the whole beam. Considering the whole beam. So this is just the force coming down. This is negative, going down as negative, going up as positive. So negative, positive. EY is the one already calculated. This one, FY is the one which is unknown yet. So FY here, negative 355 coming down. This one 44 multiplied with 105 coming down, because this distance here is 105. This distance is 105 meter. So solve this, you get Fy negative, which means the directions is actually acting downwards with the magnitude 66. So with this, we solve for all the unknown forces, Ax and also Ay, By, Ey, and Fy. And again, if you want to do checking, so these are all the forces already calculated. So if you want to do the checking, Ax is not indicated here because Ax is equal to 0, but in the solution process, you have to calculate. So you take moment at C, this is for checking, then you consider the moment caused by all these forces and all this, and this distributed load, UDL at point C, considering the whole beam. the three-span beam, you should get almost equal to 0 or 0. Then it is a kind of checking that all these 4521797369666 kilonewton with the direction down, up, and down is correct. So that is cases of beams with hinges where they are located at different positions along the beam. Case 1 and case 2, which I call it here. But class, the basic principle are the same. They are both statically determinate beams, and that's why only equilibrium equations are needed. The difference between case 1 and case 2 is that in case 2, we cannot find a free body diagram or where you can write down equilibrium equations and solve one of the unknown forces directly. We cannot. We have to write down, we have to solve simultaneous equations for this particular case 2. That is the difference. But the rest, the principal use, equilibrium equation, cut at the hinges, form equilibrium equation at the hinges, they are all the same. They're all the same. Okay. So today what we have covered is we look at examples again on statically determinate beams and frames, and I have gone through 2 examples of frames with you, and also we go through example of beam with hinges, how to get the support reactions. And when there are hinges, surely you need to make use of the conditions of the existence of the hinge in the solution process. So that is things that I have covered today. And before I end today, I would like to show, I would like to bring up these things that we are going to discuss tomorrow when I see you again, which is frame with inclined members. We are talking about frame with inclined members. Just now in the class we discussed frame where all the members are either horizontal or vertical, as shown on this photo here. Frame with only vertically or horizontally oriented members. So members are either vertical or horizontal. But there are many cases of frames. If you happen to pass by, I think remember when you pass by factory, when they are construction site or factory, normally you will see this kind of steel structures where there are some members which are inclined. There are some members which are inclined, especially at the roof level. They want to create an inclined roof. So there are members which are inclined. So in this case, you have this frame where it consists of vertical member and inclined members. Vertical members and inclined members. So the next thing that I will be discussing with you tomorrow is how do we consider cases of frame where there are members which are inclined. There are members which are inclined. Okay. Now, as a start, this is the thing that I would like you to look at. This is a frame. This is a frame where it consists of one horizontal member here, simply supported here at point D. Acted, there is a load 10 kN per meter UDL acting along C to D with 2 meter. Then this member slanting, inclined, and going down with inclination of 4 to 3, or going down 3 and then you move 4, inclination 4, 3. Inclination of 4, 3 until point B here, which is a roller, and along this line, there's a load acting vertically, same like this, vertically, but along this inclined member length. Then after that, the final one, this is a overhang here, A to B, with distance 2 meter and acted by UDL 10 kilonewton per meter. So here I would like you to look at, we are going to use this example, when there's an incline, how do we consider forces acting on inclined member? So calculate the reaction forces at support B, which is a roller, and support D, which is a pin. So pin here, if I draw a free body diagram, we have this vertical and horizontal. Horizontal, okay, vertical and horizontal. And at point B here, we have one vertical. Horizontal, immediately we know they are zero because there are no other loads which is acting in horizontal direction, all vertical. So this is zero. So only thing is, what is dy here? What is by? So this is for you to think about, and then when I meet you again tomorrow, so we will go through this frame where the members are inclined in more detail. Okay? So that's what I want to cover today, class. And for tomorrow, we have 8 to 9, which is our supposed to be tutorial class. And then we have 9 to 10, our lectures, okay?